Hello once again, BC Calculus students at Avon High School. We're going to take a look at section 9.5, alternating series, and in particular with this example 1A, the alternating series test. And sort of to set things up here, as your notes would indicate, if you have them in front of you, they mention something about up to this point, most of the series that you have dealt with in the first three sections, 9.2, 9.3, and 9.4, have predominantly contained the positive terms. Your nth term was always greater than 0. And what we're going to discover in this section and beyond is various nth term expressions and summation quantities that both contain positive and negative terms. And the simplest of these types of series is called an alternating series, and it's given the name because of the fact that it alternates signs. And if you take a look here, I've altered the notes just a little bit, and I've moved the theorem 9.14 box alongside example 1A. But it's pretty much going to be obvious that you're dealing with an alternating series because of the fact that you're going to see this negative 1 raised to the n power component in your summation expression, or perhaps you could see a negative 1 to the n plus 1 component. Now, I wouldn't start worrying about the difference between the two. They really don't have a big difference, other than the fact that in the case of the first one here, negative 1 to the nth power, for n values that start with 1, you'll notice that you'll have a negative sign for your first term, because negative 1 to the first will stay as negative 1. But when you have even powers of n, that negative sign will go away because you're either squaring or raising to the fourth power or so forth. So in this instance, in the first instance here, we're talking about negative, positive, negative, positive, negative, positive in that order, where over here we would start with a positive and then begin our alteration, or our alternating. All right. In example 1A, we're going to determine the convergence or divergence of this particular series. And you'll notice that all that needs to be met are simply two conditions. Number 1, the limit of the nth term as n approaches infinity, or it should be 0, and that's a little bit of a typo in your notes. That x probably would make more sense as an n. Now, if you think about that, that might kind of bring back the nth term test to mind. And if you remember, the nth term test was always sort of a bummer when we got 0 for an answer, because it meant that the nth term test failed and that you couldn't say that your summation or your series was divergent. But now we want that nth term test to yield an answer of 0. Now, it doesn't work if only condition 1 is met. So if you do have your limit of your nth term as n approaches infinity to be 0, you must also verify that condition 2 is met, and that simply says that a sub n plus 1 is less than or equal to a sub n for all n. Now, it might be a little bit easier to rethink what this means. I'm not a real big fan of the way that this is presented in your textbook. It's presented in a variety of ways in various textbooks, but basically they're saying that any subsequent nth term expression would be less than a previous nth term expression. That's just a fancy way of saying that your nth term expression is decreasing. So you could think of this as just a sub n decreasing. In fact, if you think about it, that's pretty much what was going on when we thought back to the integral test. One of the one of the conditions that had to be met was the fact that the nth term expression had to be decreasing. So we'll probably attack these in a very similar format to the way that we dealt with the integral test. Okay, let's go ahead and take a look at example 1A. Now you'll notice for the first criteria here, it doesn't mention anything about the alternating component to your expression, the negative 1 to the n or negative 1 to the n plus 1. So what you're going to be able to do is just, for the time being, pretend that that guy doesn't exist, and just simply focus on your nth term as being 1 over n. Now, we know a little bit about that, right? You know, it's going to be very easy to verify condition number 1. Is the limit as n approaches infinity of 1 over n equal to 0? Well, I think it's rather intuitive that 1 over n is going to become 0 as that n grows very large. It probably doesn't require the use of L'Hopital's rule, but just to make sure that you're aware, if you do take the derivative of the top, you would get a 0, and if you take the derivative of the bottom, you would get a 1, and then, of course, there's no n to replace with infinity, and you get a result of 0. So we're pretty sure that we do have a limit of 0. So condition 1 is met. Now for condition 2. There's a couple of different ways that you can tackle this, as I said before. If you think of it the way that your textbook presents, all they're merely suggesting is that you find an expression for this a sub n plus 1, which means you would replace your n with n plus 1 and compare that with the nth term expression, which in this case was 1 over n. Now, what you're hoping for is a less than or equal, which I will question here. You're hoping to have that relationship. Well, once again, it might be rather obvious that 1 over n plus 1 is going to be less than or equal to 1 over n, particularly for n values that are 1 and bigger. The idea behind it is the fact that as this denominator here is viewed as being larger than this denominator, it will end up making this fraction smaller. Now, I would have to say that this is a pretty obvious comparison, and they may not all be this obvious. So just to give you another option, don't forget that we can always rename our nth term expression in terms of x and actually call it a function f of x. So we could say f of x excuse me, is 1 over x. All right, now from this line of thought, we could go ahead and take the derivative of our f. The derivative of 1 over x is, of course, negative 1 over x squared, and then it probably becomes pretty obvious that this derivative is always going to be less than 0 for pretty much any value of x, and particularly for the values of x that we are going to be concerned with here. X is greater than or equal to 1. So because of the first derivative being negative, you know that your function is going to be decreasing. So no matter how you want to go about thinking of it, you've got criteria 2 that has been met. So if criteria 1 is met, criteria 2 is met, we notice that the conclusion here holds, and that is that this particular series will converge. Now, I can't finish this example without sort of giving you guys something to think about. Cover up the negative 1 raised to the n plus 1 power for the time being. In fact, I'll use the highlighter to do that. If we cover him up, pretend he's not there. What do you know about the summation of 1 over n? It's the divergent harmonic series, correct? Do you find it interesting that by adding, I should say, this alternating component, putting it in front of the harmonic series 1 over n, we now have something that converges. So, sort of to sum up, the harmonic series 1 over n diverges, but the alternating harmonic series 1 over n converges.